All right, folks, here we go. Today we're going to get to start a brand new type of function. Okay, it's called the exponential function. Notice the form of the function right there is f of x equals b to the x. Now, b is a number. Okay, it's constant. It'll never change in each problem. X is the exponent. It's the independent variable. Okay, so again, we're looking at a function, f of x, which is equal to b to the x. Okay, our independent variable is now in the exponent. B is going to be any number that is greater than 0 and not 1. Okay, let's look at an example. All right, before we begin with exponential functions, let's review, just for a second, negative exponents. Okay? So remember, a negative exponent indicates a reciprocal. So we put 1 over that value. So you can see here, when we have x to the negative second, we really take the reciprocal. We take 1 and we divide it by x squared. And now there is no longer a negative. So if we do a problem like 2y to the negative third, and we want to rewrite it, remember the negative 3 is only on the y. The 2 stays in the numerator. The y cubed goes in the denominator. Okay, the second example, again, the negative 1 is only on the y. So the 4x stays in the numerator, and the y goes in the denominator. Okay, just going to have to use that fact in some of our problems. Okay, so our first example here, f of x equals 2 to the x. I'm going to graph that out using these x values right here in the chart. So if x is negative 2, I'm going to have 2 to the negative second. Remember, the 2 goes in the bottom. Reciprocal, it's squared, so that's going to be 1/4. 1/4. Now we're going to a negative 1. Again, reciprocal. 2 goes in the bottom to the first. 1/2. Now we're going to the 0. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. Okay, now I'm going to graph to get what shape we have. So 3 is 8. 2 is 4. 1 is 2. 0 is 1. Negative 1, 1/2. Negative 2, 1/4. And they would keep getting smaller. But we have a curved function here. Okay. It shoots up very fast, approaches the x-axis, but never touches it. That's very important. Okay? That line has a special name, which we'll get to in just a moment. Back one. Okay? So if you notice on that graph, okay, now our graph, if we look at it, as x values decrease, in other words, as I get closer and closer and closer to 0, the function is leveling off and getting closer to the x-axis. Right? So there's your x-axis from the previous page. My y-axis is right there. Notice it never hits 0 because it never hits the x-axis right here. In this case, the x-axis is called an asymptote. Okay, so that line is an asymptote. Sometimes in math, to even specify it more, it could be made a dashed line. Okay, that's called an asymptote. An asymptote is a line that a graph function approaches at the x values get very, very large or very, very small. Now, a couple other items of note. If you're dealing with a function that has a number a times this exponential or times b to the x, okay, it looks like that. It could mean it like 10 times 3 to the x. Okay. We know some things just by looking at the equation. Okay. If the b value is greater than 1 and a is greater than 0, then as x increases, the function increases. Okay, so it's going to kind of go up this way, rough sketch. Only if b is bigger than 1. If, however, you have an example where we have something like 22 times 4 to the 1/2, now the exponent is less than 1. So it's decreasing. And I already know what my graph should look like. Something like that. The only other thing to remember here that could be of a big help, the a value. Okay? The a value. A ends up being the y-intercept. So you end up with an ordered pair, 0, a. All right, here's another example we're starting with. 10 times 3/4 to the x. So two numbers to figure out here. We got the 10 and we got the 3/4 to the x. So in this problem only, the a is 10. That's also your y-intercept, 0, 10. Okay. If I put 0 in, 10 times 3/4 to the 0 is 10 times 1, which is 10. 0, 10. Okay. The other value I need to take notice of is b. b equals 3/4, which is less than 1. So this is going to be a pk problem. All right, let's put some numbers in. Make a table of values, please. Use these same numbers. I'm going to have 3/4 to the -2 times 10. 10 times reciprocal 4/3 squared. 10 times 16/9. All right, so we can also plug in the 0. 10 times 3/4 to the 0 is 10 times 1, which is 10. Oh, for the 2, -2, 160 over 9. This is about 17.7. Okay? 10 times 3/4 squared. 10 times 9/16. 90 over 16 is a little more than 5. Okay, I'm just going to punch it into my calculator and get that quick. So we have an idea when we graph it what the decimal is. .625. Notice the numbers are growing smaller because it's decreasing. Okay. We put in a 4. 10 times 3/4 to the 4. Now these numbers are getting pretty big. 10 times 81 over 256. If we multiply by 10, 810 over 256. All right, so we keep going. We had the 810 over 256. Okay. That's going to give us about 3.16. Okay. That's probably good enough for right now. -2. So let's focus in on the graph now. -2 is going to be up here around 17. 0 is at 10. Already got that point there. 2 is 5.65. 4 is 316. And I can see the general shape already. Remember, it's decreasing, gets all the way, but does not touch the x-axis. Again, that x-axis is called an asymptote. Sometimes you'll see a dashed line on the graph for an asymptote. All right, now we're looking at some modeling, okay? Using math to make predictions. Okay. So we can model growth or decay by a constant percent increase or decrease with the following formula. So the key is going to be knowing what your R value is, adding it or subtracting it from 1. Our variable is going to be t. T is our independent variable. Okay? And A is just going to be another number. But it's going to be a special number. Okay? A is always going to be what you start with in the problem. You put it right in here for A. Then R is your rate of increase. That's when you use a plus. If it's rate of decrease, then you lose a negative, a minus. R plus 1 is growth. R minus 1 is decay. Right? Let's do a model. So, in this problem, Claire's going to invest $5,000. Okay? So the initial amount that she's going to start with is $5,000. My strategy for word problems is to write things down as I go. It paid 6.25 interest every year. So that's an increase. So our R value is positive 0.0625. Okay, it says how many years will her investment be worth after 10,000. So I'm going to want to plug 10,000 in for T. Okay. My equation, remember, is the amount equals A times 1 plus R, because this is increasing to the T. So our equation here will be 5,000 which is A, 1 plus 0.0625 to the t. We should simplify that and clean it up and make it 5,001.0625 to the t. There's our equation. How many years will our investment be worth 10,000? So I'm trying to figure out if I take my equation and set it equal to 10,000. Now for a problem like this, we're going to go to Desmos. All right, so when I graph these two, they end up intersecting right here. When we graph and figure out that point, it will happen in 1.428 years. Okay. 1.428 comma 10,000 is the point you're looking for on Desmos. All right, finally, last problem of the day. Now we have a city population, which was initially, so remember, whenever you see that initial value, 15,500, that's going to be your A. So our equation is going to be y equals 15,500, not 15,000. That's your A. Our B value, we're going to have to calculate. It's going to be 1 minus 0.03 to the t power, because this one is dropping or going down, so that's why it's subtraction right there. I can clean this up a little bit and say that my equation is y equals 15,500 0.97 to the t. Now it says, when will the population drop below 8,000? That's a y value. Okay. I could put numbers in for t to get close to 9,000, or I can use Desmos. Now on Desmos, remember, you're going to graph the equation, the 15,500.97 to the t, or x. Then I'm going to graph y equals 8,000. I'm going to see where they intersect. Okay, your assignment is posted for this video. Make sure you do that assignment over the weekend. The assignment itself is located on GoFormative.com. Thank you.